Double.
Would it be doob or daub, according to the English?
I feel like I can use that somewhere.
I think you could use both.
You've done so much.
But I think
forgot your
doob would be
English.
D-O-O. I think that would be dab.
Daub.
D-O-O would be doob.
No, it's not doob nor dub. It's dub.
Dub.
That's a double.
Huh. Double integrals.
So,
Can we bring in an English major on that?
sure, why not? Okay. Okay. 14, okay, so 5 people missing. Now, what you saw from the last section is, and this is much more challenging, double integrals as opposed to single or regular integrals from Cal 2, is just the setup. How do you get the limits? Because once you have the integral set up, it may be tedious from that point, but at least you know exactly what you need to do. The setup is it's not something where I can describe an exact algorithm, and I know that's something that frustrates many students, but tough. That's really actually a fundamental aspect of math, and there isn't always an algorithmic approach you can take, no matter how much you might want there to be one. Now, polar coordinates is meant to actually make this easier. That sometimes using polar coordinates, r and theta, it's easier to set up the integral than sticking with x and y. So we've come across polar coordinates before. If we have this is a refresh your memory, we have a point x, y, and so these are Cartesian coordinates. Can also be expressed in polar coordinates r and theta, where distance from the origin is your r, and the angle the point makes from the positive x-axis is theta, and we have the conversion, x equals r cosine theta, y equals r sine theta, and then going the other way, r is square root of x squared plus y squared, and theta, and tangent theta is equal to y over x. Okay. So the idea is if you're given a description of a double integral, like for instance find a volume of a certain solid, like we've done a few times. So based on the region you're integrating over, it's especially when you have, if it's described using like a portion of a circle, maybe x squared plus y squared comes up in the description of the domain. That's a sign that it's a good idea to convert to polar coordinates. So the integral of your given function f of x, y over your region D in the xy plane, which you would normally work out as some sort of iterated integral. You'd figure out limits for x and y. That would go here. Instead, we work out as an integral over the same domain, but now expressed in polar coordinates. So you fill in your integrand, x becomes r cosine theta, y becomes r sine theta. So you make those substitutions directly into x and y in your integrand. And then you might think, okay, we have dx and dx dy before, so now you're going to have dr d theta, but that's not everything. Do not forget this extra factor, r, that has to be included. This actually came up on the very first day of the semester. I had a double integral in x and y, and I converted to polar coordinates, and that introduced this extra factor of r. And without going into too much detail right here, the reason for that is, if you think in terms of the r theta plane, so these coordinates, if you have what's called a polar rectangle that has sides delta r and delta theta, but if you keep in mind that this integral came about as integral with respect to x and y, so so your element of area is not going to be just delta r times delta theta. Under a change of variable to Cartesian coordinates, what you're actually going to get is this portion of like an annulus, like two concentric circles, and this gap here corresponds to delta r. But change in angle here is your delta theta, and depending on where r is, like this could be one region to which this polar rectangle can be mapped, or it might be something down here, and we want the area of this piece that I'm shading in, or this piece. Just a couple different examples. And what you notice is that as you move further away from the origin, as r increases, these regions get larger. So the same values for delta r and delta theta still lead to different areas depending upon how far away you are from the origin. The area of this little wedge here is actually proportional to r. So that's why we have this extra factor of r. Now, I'm going to refer you to page 83, 84 of the notes, where I explain more fully where that extra factor of r comes from. So it's worked out a bit, well, actually just page 83. It's all there. Why we have that extra factor of r. So if you're curious, you can look at that. I want to focus today, in the notes I have several examples of how to work out polar integrals, and that's of course what you're going to be doing on the homework. But the point is, when we make any kind of change of variable from xy to anything else, there's going to be some sort of extra factor that has to be included. So it's going to be r in polar coordinates. Later we'll look at three-dimensional coordinate systems, cylindrical coordinates, where again it'll be r. And then we'll also look at spherical coordinates, where it'll be something else. And then other changes of variable. And for all these cases, you can figure out what it's supposed to be, and we'll see that later. But that's one of the most common mistakes, like on a test. If you're asked to evaluate integral in polar coordinates, you figure out your limits, you figure out your integrand, and then you forget that r. Don't forget that r. Okay. Now, oh, by the way, just made this change. The homework that in MyLabs Plus is currently due today, or was due today, I've pushed back to tomorrow. Okay. So your integrand is x plus y, and the region D is a set of all xy such that x squared plus y squared is greater than or equal to 1, less than or equal to 4, and x is less than or equal to 0. Now, when you see that x squared plus y squared, that suggests that we're dealing with a domain that is circular in nature, which is one of the situations where you most likely want to switch to polar coordinates. So if we visualize what this region is, so the boundaries of this region are x squared plus y squared is equal to 1. That's pretty good. I have my moments. And then x squared plus y squared is equal 4 for the outer boundary. But we only care about x less than or equal to 0. So your region D, I'll just shade in here, is this part. All right. Is there a question?
No, it just looks like a donut.
Oh, yeah. Thanks for mentioning that. I wanted that donut. But, okay. So, now if we were to try to express this with limits in terms of x and y, like, that actually would be kind of a pain. In fact, you could not do it as just one integral. So if you let x go from, okay, so here the radius is 1, and for the outer circle the radius is 2. So you're going to think, okay, x will go from -2 all the way to 0. All right, so the x limits would not be a problem. But what about y? If you're over here, you'd have 4 separate bounding y values, so you'd have to break it up into 2 integrals. So your limit, like for this piece, could be something like square root of 1 minus x squared and square root of 4 minus x squared. You get these really difficult expressions. So this is why we have polar coordinates, or one of the reasons why, that we can describe a region more simply in that sense. So if we can describe the same region as a set of all r and theta, and describe bounds on r and theta, maybe we'll find that easier. Because what if you get constant limits for both? That's the easiest case of all. So keep in mind, what is r? Distance from the origin. So what should my upper and lower bounds be for r?
1 to 2.
Yeah. Because x squared plus y squared equals 1, in polar coordinates, that's r squared equals 1. So r equals 1. And then r equals 2 describes the outer boundary. So if you have a circle of a certain radius, r equals that value, that describes that boundary. Okay, and now as for theta, you know how your angles work. Theta equals 0 starts over here, and you go to theta equals pi over 2, and so forth, all the way around the circle back to theta equals 2 pi. So what should my bounds on theta be?
Pi over 2 to 3 pi over 2.
Yeah, so that covers the left half plane, where x is less than or equal to 0. So pi over 2 to 3 pi over 2. So this region that in x and y space looks like half a donut is actually a polar rectangle, because it can be described as r and theta bounded by constants on both ends. So we can write this as the integral from pi over 2 to 3 pi over 2 in theta, and then 1 to 2 in r. And then we need to substitute in our integrand. X becomes r cosine theta, and then y becomes r sine theta. And then don't forget the extra factor of r, then you have dr d theta. All right, so now the integral is at least set up. And in this case, it should be far easier to work with it in terms of polar coordinates than Cartesian coordinates. Is there any questions about just the setup? Okay. Now, I'll start you down the evaluation process, at least until it becomes, 1 or 2 relatively simple Cal 2 problems, and everything else is worked out in the notes. Because in class, I want to spend more time on the setup, because that's really the hardest part. Now, one thing you can do is look if you can express your integrand as a function of one variable times a function of another. Or even if you can't do that, maybe you can split it into, if it's a sum of a few terms, and you can do that with each term. In this case, you can, because So we have pi over 2 to 3 pi over 2. You can write this as r squared, and then you have cosine theta plus sine theta. So I've lumped in this r with the other one. And so then we have dr d theta. And so remember what I said you could do when you have your integrand as a product of functions depending on different variables. So you can separate this into a product of two single integrals. This one for theta times the one for r. Alright, so then you have two integrals that you can work out using your Cal 2 knowledge. And once you've got that, so this would be, that works out to be 7/3, and this works out to be -2, so overall you get -14/3. And it's not surprising that you get a negative answer because throughout this whole domain, x is negative. And this is, so more of the gory details you can find on page 84 of the notes, just working out the integrals from here. Any questions about this one? All right. Alright, for another, we have volume problem. And this solid is in the first octant. So that's where x, y, z are all greater than or equal to 0. And it's bounded by this surface, z equals square root of x squared plus y squared. Now, we've seen z equals x squared plus y squared before with no square root. That is a paraboloid. But then when you take the square root, that alters the shape. So this actually describes a cone. So if you have z equals square root of any of the coefficients of x squared and y squared being the same, that describes a perfectly symmetrical cone. That's radially symmetric. If the coefficients are different, it would be like if you mush the cone in one direction. It's also, it's bounded below by the cone, and it's bounded above by x squared plus y squared plus z squared is equal to 8. Of course, that is a sphere of radius square root of 8. So if I were to try to draw this, so you have your cone starting from the origin going up, and then you'd have this capped by this sphere. So basically, it's like you have a snow cone. Now, as for other boundaries, since we're in the first octant, you also have the planes x equals 0, y equals 0. Okay. So this is the three-dimensional view. If we look at this from above, just x and y, so we're only in this first quadrant, because x and y have to both be non-negative, and you have some circular boundary here, and the furthest extent of this region is where the cone and the sphere meet. So we have, so the cone is square root of x squared plus y squared, and that has to equal, so this is the z value for the cone, and it has to meet the z value for the sphere. So the sphere, if I take this and solve it for z, what's my z value?
8 minus x squared minus y squared. Yeah,
Square root of that.
Yes.
Yes. Okay. 8 minus x squared. And I'll factor out the minus in that case. Square plus y squared. Okay, so you want these two to meet. Okay. Now, so we want to be able to describe this in terms of polar coordinates. Now, okay. So we need bounds for r and theta, and hopefully these will be constant. Okay. All right, from the first octant in three-dimensional space, but that's the first quadrant in two-dimensional space. So what would be the limits on theta? What angles are the first quadrant? Yes, 0 to pi over 2. So here's 0, 8 equals 0 right here is theta equals pi over 2. Remember, we always work in radians. Okay. Now for r, we're starting at the origin, so it makes sense that our lower limit for r would be 0. But we want to use this equation that's square root. An inner square root should not be there. Okay. It needs to match that. So to find the upper bound on r here, it's going to be where this equation is satisfied. So I want to express this in terms of polar coordinates. Now, I have square root on both sides. So I can square both sides to get rid of those annoying square roots. All right. Unfortunate voices can go past through that grate. I guess if I need to, I can yell through the grate to shut up. Okay. All right. So this equation needs to be satisfied. So how can we write this as simply as possible, just the equation in polar coordinates? What does x squared plus y squared become? Like your conversions that I gave earlier. X squared plus y squared equals what in polar? R squared. Yeah, so now I'll just have r squared equals 8 minus r squared. But now I can solve that equation for r. So what would the solution to that be?
R squared is equal to 4, so R is equal to 2.
Yes. Yeah, because I can move to the other side. I have 2r squared is equal to 8. R squared is equal to 4. We want the positive square root, so r is equal to 2. So sure enough, we get constant limits. Now, I don't want to give you the idea that it happens all the time. We'll see examples where it doesn't happen, but even if we don't get constant limits, it's something that's still going to be simpler than if we had to do this in Cartesian coordinates x and y. Okay. So now we have our limits, but we need to be able to write the integral. So the volume, it'll be the integral. Now we can have either one of these be the outer limits. Just as by convention, if I have a choice in the matter, I just let theta be the outer limits. 0 to pi over 2, and then 0 to r. And we're going to have r d theta. Don't forget your extra factor of r. Now, when it's a volume problem, what does not change, it doesn't matter whether you're in terms of x and y or r and theta, is you're subtracting a difference in z values. So you have the z value for the sphere, which would be this in polar coordinates. So square root of 8 minus r squared, so the z value for the sphere, minus the z value for the cone. But that's just going to be z equals r. And so that times your extra factor of r is going to be your integrand. That's supposed to be a 2, believe it or not. Okay. Okay. So any questions about the setup of this one? To try to see how to evaluate it. So we have r, I'm going to break this up into two integrals. So r times square root of 8 minus r squared, dr d theta, minus, the way you would handle these two terms is very different. So this r times this r will give us minus r squared. Okay, now, one nice thing is there's no theta in here at all. So you can think of this as the integral of this with respect to r from 0 to 2 times the integral of 1 from 0 to pi over 2 d theta. But since there's no theta in the integrand at all, you can always write this as just the integral from 0 to 2 of everything you have in r times the integral of 1 from 0 to pi over 2 d theta. But what's that going to be? If you're integrating 1 from over what interval?
2.
It's just pi over 2. It's just the difference of the limits. So then you can just work this out and multiply the result by pi over 2. Now, what about the r part? This term, not even worth talking about. This term, how do you handle this one?
Integration by parts.
Not needed.
No.
We can do it simpler than that.
Uses.
Yes. What should the substitution be?
8 minus r squared.
What?
8 minus r squared.
Yeah, 8 minus r squared. So then du is equal to minus 2r dr, which is convenient because there's an r sitting right there. So then it becomes fairly straightforward after that. So I'll refer you to page 85 in the notes for the details on how that is worked out to see what the final answer is. Okay. Is there any questions on how that one gets started? Okay. This next one is actually all about setup. I'm not even specifying a particular f of x, y, but the focus is squarely on how do we get the limits. And sometimes you can do it by visualizing the domain, and that's what we've seen in these examples. Or other times you can work it out more algebraically, which you might prefer. So suppose you have this double integral for some generic f. Okay. Now, if we were to try to do this visually, so we're looking at x going from -1 to 1, and then y starts out at 0 and goes up to this curve. Y equals square root of 1 minus x squared serves as the top boundary. Now, can anyone tell me what kind of curve that describes? You might recognize it more easily if you squared both sides and rearranged. It is a circle, because this is the same as x squared plus y squared is equal to 1. So we're looking at, because we're starting from y equals 0 for bottom boundary, we just have the top half of the unit circle. Okay. Now, just from the picture, we could use that to come up with limits for r and theta. So this being a circle, radius 1. So what should our bounds be on r and theta?
Theta be 0 to 2 pi.
Not 2 pi.
Just
Just pi because it's the top half.
RB0.
R of 0 to 1. Okay, so that's how you can see it from visualizing the region. But that's not the only way.
So why would it not be from -1 to 1 for that shaded region?
Okay, because that's for the x coordinates, but
Okay, I see.
yeah, because negative r would take you over here.
It's just like the radius, okay.
It is, yes. Now, another way to arrive at it, which, if graphing is not your strong point, is if we look at this equation, y equals square root of 1 minus x squared, and we make a substitution, we convert it to polar coordinates. So y is r sine theta, and x is equal to r cosine theta. Okay. All right. So now what you can do is square both sides. And rearrange. But sine squared plus cosine squared equals 1. So then you just get r being 1. So that's one way to see that that 1 is your upper limit for r. And there'll be other cases where it might not be so obvious from the equation, where doing it algebraically like this can be helpful. And we'll see this in other examples too. So that could be a good idea to try that approach to figure out your limits. But if you know you're confined to the top half plane, that automatically means theta can't go beyond the interval 0 to pi. if, for instance, you're in the, we saw in the left half plane, you're going from pi over 2 to 3 pi over 2. If you're in the right half plane, you can let theta be negative, because everything's periodic. If you're over this side where x is positive, you go from minus pi over 2 to pi over 2, and so on. So if you know that your region is confined to a certain portion of the xy plane, that can give you some guidance on what your theta limits should be. So whatever you have for f of xy, you would have this integral in polar coordinates. So 0 to 1 in r, 0 to pi in theta, and you make a substitution into your integrand. And then don't forget your extra factor of r, dr d theta. Any questions on this one? Does anyone have any questions on the homework that's currently out there for 14.1? 14. Okay. Yeah. So I do have more examples in polar coordinates, but we also have time for that on Wednesday. Come on. Have the rest of you had trouble with MyLabs Plus, like with it being slow or? Yeah. I had a devil of a time because I wanted to push the deadline back last night, and it took a while just to get in.
One day it just crashed on me.
Oh, fantastic. Okay. Yeah, anytime, I'm still waiting, you just can't get in at all, I need to know about it, because especially if it's something where it's a more widespread issue, if that's something I'd want to take into account as far as due dates and such. Okay. Of course, the internet on campus is not always that great either. Okay. All right, it's logged me in, but please wait, loading your courses. I just love how apparently sometimes you just need to like refresh a page and it'll do it. And it's like, what, do you think I was kidding the first time or the second time? Yeah, it's like I can move through this if I just keep telling it to refresh. Okay. 14.1. And that's problem 14, right?
Yes.
Okay, it's been so long I might have forgotten. Okay. Okay, so it gives population densities of a rectangular county. And your numbers might be different. All right, so we have a region from, all right, so marks like y values 1/2, 2, and 3.
Oh, I hated this problem. I literally calculated it probably 4 to 5 times before I actually got it. It was terrible. And also,
It's a
somewhat
good thing I
embarrassing.
give so many attempts. Okay. All right, and then it fills in numbers like 450, 400, 400, etc. All right, and what it's asking is, okay, population is population density times area to estimate the population of a country. Oh, that's funny. They say population density is a rectangular county at first, and then later say population of a country, and then later county again. That's
It was
that's
a little ambiguous.
what?
It was a little confusing, like I didn't.
Yeah. And then explain how this is related to Riemann sum integrals. Okay, actually, I'm curious what they say about the next part. Oh, that doesn't let me do that. Okay. Okay, yeah, in this preview mode, it won't show me the second. Is the second part like multiple choice or something?
Yes.
Oh, okay. All right, good. It's like, what do you do? Write an essay or something? Or, okay. Now, I'm going to step back a little bit to single integrals so that you can then make the leap from there to double integrals. So, because a Riemann sum, we have your width, your delta xi, and then you have your height of xi star, where you're trying to estimate the area under a curve using rectangles. Okay, so here's your width, delta x1, delta x2, etc. And then you have your heights, f of x1, which in this example I'm always using the left endpoint for the height, but whatever. For instance, you have some y value that you're using for your height, and then the spacing between your x values becomes your width, and you're summing the areas of these rectangles. Now, for a double integral, it's a similar idea, just moves up one dimension, where so now this problem is about population, where your population is density times area, and just like with volume, you have the area of your base times your height. So you have a situation where you have your two-dimensional region, your base, and your base area is equal to delta xi times delta yj, because you have your x values along here, and your y values along here. And these are your x values, x1, x2, x3, and so on. So you have the same thing going on in both x and y. You multiply the area of your base, so the dimensions of your base rectangle, like one of these, times your height, which you get from your function. So your height is your function evaluated at some x value within your rectangle and some y value. So here you're doing the same kind of thing where these are your z values, which are your f values at certain x and y, where the x's and y's correspond to points within these rectangles. And just as in the single integral case, you have area equals width times height. Here you have volume equals base area times height. Here you have population, as they give you, is population density times the area. So these So this region in the xy plane serves as your base. The base is divided up into rectangles. So you're using this formula for each one of these rectangles, and you're adding them all up. Okay, so these integrals are used to take product formulas like population is equal to population density times area, and generalizing them to these cases where the population density is not always uniform. All of these values are different. Okay. So basically you're summing up areas times densities, where the given numbers are your densities. So everyone see what to do with that one. So in fact, your population estimate would be a double sum. You have 3 subintervals in each direction then. So you'd have your density in the ij rectangle times the area of the ij rectangle. So this is like your double Riemann sum. So you can see how this conforms to a double integral. So that's really what you're doing. You only have density values for these large regions. So you don't like have a formula for continuous function of x and y that gives you the density at every single point in the rectangle. So since you can't evaluate the integral to get the population exactly, what you were getting here is an estimate. All right. So you can see how a Riemann sum for a single integral generalizes to a Riemann sum for a double integral. Okay. Questions? In the last minutes, any other problems from this section? Okay, you get out 1 minute early. Woo!